work on overleaf on lecture notes. Notes now, yeah. B oral exam at the end. And one chapter. Cycle. During exam. And now these are options. All right. Now plus everyone needs to make homework. Needs to do the complete works. That's around one homework each time, each week. Okay, and around 2 to 3 coding homeworks. And if you cannot complete, are not able to complete, homework, attempt, show your attempt. And we'll discuss homework at the end. Next time. Discuss homeworks next week. Now that's basically all the rules. I didn't forget anything, right? And sorry. Yeah, so 2, like reverse cross approach, reverse investment cross. Your the videos, the next lecture videos. Videos and And I'm sad to help you. And yeah, starting time. So now we discussed, agreed that actually it will be, lectures will be lectures 15 to 17 of Eastern European time, which translates to 14 to 16 Central European time. All right. Yes, Kaspar.
Usually in your courses, the homework is a part of the grade. So what
Yeah. That's right. So I'll count. Well, I presume that you will be making all the homeworks. If you are not making all the homeworks, then we'll keep this in mind. And actually, during examination, because we have oral examination, during my other lectures here with you, we have been having a written examination, right? So now we try to just to find a consensus with you. What feels like a fair grade at the end, depending on how many homeworks you did and how much you worked on the project or how good you were at the examination. So of course, I will keep in mind how many homeworks you did. All right. Everything clear? Now, yeah, and next time I'll be not writing here like that, but I'll be having an electronic screen, and I'll be writing over that on the electronic screen. Yes.
Are the videos 3 hours long?
Are the video?
Videos 3 hours long.
Around 2 hours, yeah. The existing videos are each around 2 hours. Videos, okay, lecture videos, okay, here have around 2 hours long.
Just asking.
Yeah.
What's the point of us making presentation? Like,
now, what do you think? What would be the idea of you making the presentation?
because we're watching the video anyways.
Well, there are two different things. One is when you just watch, then you think, okay, this is fine, okay, that's it. But if you need make a presentation by yourself, then you definitely need to understand better. So because
then we run into the problem where each time there's a different person that's making the presentation. So I'm just gonna focus on like learning for my own presentation and not other subjects. Like,
okay, just let us try this way, because those guys who are working on how to teach, they believe that it's a good approach. We'll see if it's good or not. This, for me also, like first time more or less trying.
it's just logic.
No, but you will still learn a lot. You will still learn more listening to your classmates in front of the class than looking at the computer. If you don't have to make the presentation yourself, you will just learn from the classmates.
Yeah, that's what the thing is. That's what the motivation for having this way is that you have lectures already videos. So of course I can I would be able to tell exactly the same thing next time as well, but how much sense does it make? So just repeat what I did last year. So this you can look at the videos. So that would be just like telling the same thing over and over and over.
But the problem is like the way people usually learn, like, let's say at 20% of the lesson I have a question.
20% of time?
And like let's say 20% of the lecture is over and I have a question.
Yeah.
20%. That like is very important to my whole understanding of the topic. Now for videos, I will have to watch the whole video, be confused about like the other 80% of the video. Like while in classroom, I could just ask the question, you could explain it to me, and I could just follow along then. But like that's my problem with video learning, and if I can't ask questions in between,
Okay,
I
so
will be confused about the subject.
all right. So yeah, your presentation, what you definitely don't need to do is like tell exactly over what I did. But you need to your presentation is expected to something like you pick up the most important things maybe there, or something which like give your view on the things over there. So or maybe raise questions which seems like questionable, and so during your presentation you can also raise questions. Yes.
Is there some kind of book that the course follows? That we could
Yes, what it follows is exactly those lecture notes, because with, there is no book which satisfies, in my opinion. There are a lot of books, of course, on turbulence, but they are mostly very mathematical. What our aim here is to have more qualitative explanation of turbulence things. Of course, we cannot avoid math at all. We still definitely do have some math, but we try to keep things whenever possible at intuitive level. Like you need to understand what is going on intuitively and not so much mathematical. And that's why there are not really no existing textbooks which fits what we plan to do here. But we do have lecture notes, and we have lecture recordings. There is one book so which is recommended, and I think there is at least one copy also available in the library. It's Zinnaber's Informal Introduction to Turbulence. This is also in the, I think this is in the written in the link. Name is reference is given in the course description. Yes, Jürgen.
How many presentations students?
Well, we have 16, so we need to distribute them between you, or depending now if those Eurotech students will join, then there are like something 8 or 9 students there. So my idea was that at least you work in pairs for next lecture. But of course, if you prepare to work alone, that is fine as well. But if you work in pairs, something like 4 pairs, maybe around four presentations in that case, in the best case. But if it depends on the number of students. And again, don't worry too much about your presentations, because we do have lecture notes, and your presentations are indeed aimed to just yeah, Kasper.
We have only half of it. You said only 7.
No. Okay, I can. There are more lecture notes than just 3. So 7. Let me open and tell you exactly. So out of 15 lectures, we have chapters 1 and 2. Then we have 3 and 4, and 5 and 6 and 7, and 8 and 9 and 15. So we don't have 10, 11, 10 to 14. We don't have. So we don't have 5 lectures towards the end. And that's actually where it comes into play, that point A here. So, but we do have lecture recording for those. Yes.
I have a question. The lecture notes and the videos, how do we get access? Do you like send us an email or?
Yeah, I'll be sending also the links to you by email. So yeah, let me update what is written here. We add here now.
Should we maybe like distribute chapter or on overview? Because like.
Distribute what on once again?
Maybe we should like split up the chapters between the groups.
Yeah, sure, exactly, exactly. That's the way to go there. So there are options of working on the new ones and improving the old ones. So it's up to you to decide and break up into groups and all that. So let me also write all these here on the whiteboard so that everything becomes somehow documented.
Instead of presentation, wouldn't it be better if we just split the lecture notes between each group, and then it would have the same effect as having presentation, because you still need to focus. Like let's say each group tries to improve, like every group has their own lecture that they do.
Yeah, well, I agree completely that shows if now let us see the overall picture. So raise your hand if you plan to work on the lecture notes rather than giving full exam. So it seems that everyone is willing to work on the lecture notes. In that case, of course, those chapters which your group picks, of course, you will make presentation on those. That's definitely. And then I think it would be fair that those who take lecture notes which have nothing written before, they have a smaller number of lecture notes as compared to those which already do have something. Yes?
I mean, maybe split it, because since there are 4 chapters that aren't written, we have 4 groups.
Yeah.
If we can give each group 1 chapter that isn't written.
Yeah, that's a good idea. That's a good idea. Yeah, that's a good idea. But we'll always see how many Eurotech students are there, and just so it all depends. From that I expect also from you a certain kind of self-organization here. But yeah, that's what.
Well, we can't communicate with the Eurotech students.
I think we need to create certain platform, and actually there is a platform already because overly there is also chat possibility on overly.
But maybe it would be better if we just
assign.
See by the next lesson.
Yeah, step by step. I think we can make assignments step by step regarding lectures and so on. Okay, so what did we want to write down here now? It was books. Books. Formal. Because no voi valita. Description, yeah. But this covers only a small part. A small part. Now, our aim. Our aim is to explain things plain and understand. And qualitatively. By avoiding excessive math. Excessive math. I think math is possible. And possible. Existing textbooks mostly mathematical. Now, because of that, our source lecture notes. Notes with reference design. Plus lecture videos. All right. So no, but I dropped out of. I know. And what else to discuss? While working on the lecture notes, lecture notes. And presentations. Use chat at the web. All right. Is everything now? Yes.
Maybe you should specify that we should split.
Okay. Yeah. I split it about. Integrals. And about. Do I need to write the presentation is on the topic of your election of the kind of object, right? All right. Anything else? Hopefully everything. And then maybe we still have some time to definitely we do have some time to have now more. We now are going because it's first lecture. We're going to repeat the first lecture on the YouTube right now, just to use the available time and maybe have questions. So this kind of what will be going on now is an overview of our course, which we'll be having here. The summary, so to say. We are not going to much details, but just a general overview of the course. Now, course is turbulence and mixing, and it has two words: turbulence and mixing, and so it's a course. So now a structure of the course. This is basically also the structure of the topic itself, so turbulence and mixing. So turbulence can be divided into two parts. Let us say one is turbulence. A and B is mixing, but of course, those two things are actually interconnected. Because turbulence actually is equal, like that. Mixing of a certain vector field of a vector field. And because of that, we start with mixing. Because for turbulence, we need to have some idea about mixing. And so we first divide mixing into different possibilities. So we can mix something which is as simple as possible, and this is scalar field. Now, B maybe it would be logical to have first here this one and this one. So maybe let us swap. Let this be A and this be B, because the ordering will be from A to B. So now A, first topic, I. I is mixing of passive field. So can any one of you tell me or suggest what might be passive field which is being mixed? I will passive. Sorry, now I just passive of mixing of. Let me split it different. So the mixing of scalar fields, fields, and these scalar fields are still divided into passive fields and active fields. So what are passive fields and active fields? This I'll be explaining to you soon. First, any examples of scalar fields? Scalar fields which can be which are being mixed. Maybe what? Diffusion of what?
So maybe temperature.
Yes, temperature is one example. Exactly, temperature is one example. So now let me see if I have some other color and also writing on the board. No, I have it here at least. That might sometimes not very good looking from distance, but let's see. Scalar fields like temperature and what else? Yes, concentration of something. Concentration of a dye. Concentration of something. Sorry?
Isn't all diffusion?
No, diffusion and mixing are different. So diffusion is just a random walk. But here we have not only random walk, but we have advection. So to say that fluid carries them. So this is not poorly diffusion. Diffusion can be there, but yeah, that will be also discussing later. But it is definitely not only diffusion. Now, but then about passive and active. Any idea what does mean passive? Passive scalar field. Active and passive, just as the word means. Passive is that the field itself does nothing, right? If you are passive, sitting just over there, looking on the whiteboard, not writing any notes, then you are passive, right? So if the field does nothing, does not affect the field itself, then it's called passive. On the other hand, if the field itself, presence of the for instance, some chemical compound over there will make the fluid flow different, then it is active. Now, if we speak about those examples here, then if we have a dye, concentration is low, then obviously the effect on the flow is almost negligible. We call it passive. If you put a little bit ink into flow, water flows as it flew before. So it is passive. So does not affect the flow. Affects the flow. Now, active is contrary does affect. Now, if we have some dye, it doesn't affect, but maybe if you have salt, which is a salt solution which has higher density, then it might affect, because it will just start falling down and causing additional flow by instability. So here, for example, we have a dye with low concentration. Now, if it does affect, then the first example is like a salt solution with higher density. But again, if we have temperature differences, then warmer water is also less dense, and then it might also become active. So if temperature differences are small, then it is passive. Yeah, but if temperature differences are big, then it starts affect. Big temperature differences is also can become somewhat active. So here there is now a really sharp transition from here to here. Just this might start sometimes we can neglect the inverse effect of the concentration of the flow. Or it is, but it is so small that it does not change things qualitatively. Maybe only small percentage of something of the value change, but no scaling laws will change. But sometimes it becomes important. So it's just depending of which of the parameter values. Now, what we'll be doing here mostly is the passive scale. We have a little, we'll just mention also active, but mostly passive fields. Why is that so? Because, well, you can do more math with passive. Passive is much more simple, but because active fields usually are still in most cases kind of, or to certain approximation, can be considered as a passive, like temperature differences, then we can apply those results also to a certain degree in this case. Furthermore, you can also say that in the case of passive fields, on the one hand, we need to take as input the velocity field statistics. So we take at the input the velocity field, and the output we need to predict how the tracer will behave, how will the dye field evolve in the field. So now, if we have active fields, as long as we do know how the velocity field behaves, then we can treat this almost as the passive fields. Just the velocity fields here and there might be different. We need to take at the input, we take at the input the velocity statistics. Output predictions regarding the tracer field. The scalar field. So I can carry L1 time to here. Just might need to change the input field. To adapt to the effects, to the reverse effect, to the feedback. Feedback of tracing of a scalar field to the flow. Okay, so because of that, we can focus on here because we need all we need to know is to be able to predict how the scalar field behaves if we know the velocity field. Now, so study mostly this. This is our first big topic. First big topic. But as mentioned, this is big topic. So it means that actually this itself also has different subcases. So there are differences now. AIA is smooth velocity, small velocity fields. So what does it mean? It is more or less quite similar how you mix sugar in your teacup. So if you have a teacup, then the water flow is quite regular in that. So now what does mean regular and what does mean irregular is that the streamlines are smooth. So smooth means that streamlines are smooth. You to understand what means streamline. What is meant by streamline? Just you point a water parcel and see how it moves. So trace of it is stream, basically. So if smooth, which means like something like that, maybe it turns around, it doesn't something like that. Now the other case is A R B non-smooth, which basically means fractal. A streamline. So it's something like maybe something. So if you zoom in, it's still zigzag. It is zigzag at big picture, and then you zoom in, and if you zoom in, it is still zigzag. Still the same zigzag. So self-linear, you zoom in, and what you see is statistically the same as at the big picture. So now, why do we have such kind of seemingly exotic cases like fractal field line? Actually, it appears that it is not exotic at all, because in fully developed turbulence, you have always like that. In fully developed turbulence, always. Fully developed. Fully developed turbulence have non-smooth field lines. And how scalar fields behave in non-smooth fields and smooth fields is completely different. So that as you can see, when I mentioned that turbulence is like a complicated topic, and in particular already the mixing of passive fields, passive scalar fields is a big topic. Then it can be seen from the fact that we just need to change the velocity field characteristics, and the behavior is completely different. So yeah, so first, if we break down into lectures, so we'll be having lecture on AIA and on AIB. And then now I need more space here. I think I'm going to clear whiteboard from above. Passive fields don't stop over there, but we still have options for scalar fields. Here, actually, that's one. We assume that the velocity field is incompressible. But in AIC, we take compressible velocity fields. Now, incompressible is divergence of V. So velocity field as a function of coordinates and time. V as a function of coordinate vector R and T. So if we have divergence of V equal to 0, then we have incompressible. But if divergence of V is not 0, then actually we can compose the velocity field into so-called solenoidal and potential components. We say that V equals now V compressible plus V incompressible. Which means that yes, let's say potential V potential and V solenoidal. Potential and solenoidal. Solenoidal, what does it mean? It means that just like the solenoid magnetic field is incompressible, divergence of V is 0, right? That's why you say that it is solenoidal if it's incompressible. But potential, it means as what I mean that we can express this in terms of potential. P is minus gradient of certain field phi. But the solenoidal we can express in each term as in terms of vector potential. the solenoidal is curl of vector potential. And then compressibility is defined basically as the ratio of those two. Compressibility, let me write it like that. It goes from 0 to 1, which means that compressibility 0. Then we have a V potential is 0. Compressibility 1 means a V solenoidal is 0. Fully compressible if we goes on. And now it turns out that actually behavior of scalars in compressible and incompressible fields is also completely different. Now, can you suggest give examples of compressible velocity fields? I think it's very easy to give an example of incompressible because water flow is incompressible, right? Water cannot be compressed. But can you give examples of compressible velocity? Any idea?
Gas. Gas.
Yeah, gas. But a gas flow, atmospheric flow, is still in most cases basically incompressible. Because if you take a gas parcel, you might be able to compress it a little bit, but then pressure will become bigger and it goes back. So in long term, the volume cannot shrink. So as a matter of fact, because of that, behavior in gas flow and water flow are very similar. There is no big difference because gas parcel, it's kind of slightly compressible, but not significantly because gas parcels cannot be compressed limitlessly. Furthermore, as long as you have Mach numbers smaller than 1, actually compressibility of air is very small. Even the volume cannot shrink much. So with all that in mind, do you think you can provide examples of compressible velocity fields? Not really, but actually there is very example which you can just you don't need to go into very exotic things, but actually there is case when you can see compressible velocity fields and how mixing happens with compressible velocity fields. But yeah, I agree that it might not be that easy for you to figure it out. And so if you have no idea right now, then I can as well tell you. It's still associated with water. Maybe I give a small hint. It still deals with water. How can you have a compressible field with turbulent water?
Is there like some gas dissolved in the water or something?
So, okay.
Maybe like gas that is dissolved in the water or something like air bubbles or.
Nice try, but not. No. Well, actually, it's not completely wrong because gas bubbles somewhat, but I'll talk about it a little later. All right, just a few more moments for you to think. Actually, it's very simple case. Simple situation. Perhaps in a situation where you have seen actually how mixing of things happens more often rather than in the case of of compressible, incompressible. It's quite easy to actually to observe how happens mixing in partially compressible velocity fields. Okay, one more hint that actually once when I spoke about mixing in water and said that this is incompressible, this means that we look at this three-dimensional velocity field in the water. So water motion is three-dimensional. But now this example, what I am talking about, this is with a two-dimensional velocity field. And is dealing with three-dimensional velocity flow of the water.
Laminar flow.
Huh?
Laminar flow.
No, not laminar. Laminar is yeah, it's boring. Laminar flow is boring. Kasper has some idea, it seems to me.
And it is that when you compress water together, like you do things.
No. Should I tell you now? Okay. All right. So the velocity field at the surface, top surface of water. If we have a three-dimensional flow of water, so here is a bulk of water which flows somehow. Maybe turbulent, fully developed turbulence, maybe just chaotic flow, doesn't matter. Three-dimensional flow of water. Now, here moves water like streamline, something like that, and something like that. And now, if we take look at the two-dimensional velocity field here, because water dives inside down, then two-dimensional field here is becomes compressible. Divergence can be negative or positive. So the 3D we have incompressibility. dvx plus dvy, dvx over dx plus dvy over dy plus dvz over dz is there. But if we express from here the two-dimensional velocity field components, then the divergence, two-dimensional divergence over x and y of v equals to minus dvz over dz. And now it depends all on the value of dvz over dz. So it's positive, we have negative divergence, and the other way around. So the flow at the so-called free slip surface of the water is a partially compressible one. And it appears that actually here compressibility is around 1/2. So compressibility here is around 1/2. And this makes big differences. So if you put the sugar into water and mix, then what is the end result is that everything at the end of the day is more or less homogeneously mixed. Sugar concentration is everywhere more or less the same, right? But this is your everyday life experience, right? Yes.
Could you explain the 2D one? It's divergence.
2D. This is dvx over. This is 2d1 is this one here. Okay. This is this one here.
Again, the other side of the
dvz over dz. So just I take this equation, carry this dvz over dz to the right hand side. Now, this is what everyday experience tells you, that sugar will mix and you have sweet water. Yes, Gaspar? Ah, but you mix it. Yeah, it falls. If you don't mix it, it falls to the bottom. But I said that if you mix it well. But then if you put things on a water surface and start mixing, then what happens is that they start gathering into batches. Like if you look behind the boat, there are usually a lot of bubbles coming up because the screw of the boat will make a bubbles which rise up, or maybe some parts of the boat which when moving makes those. So there are a lot of bubbles, and then if you look where the bubbles are, there are regions of water surface where there are no bubbles, and then there are basically places where there are a lot of bubbles. So this will give rise to so-called patchiness. So this one, this is okay, from here. So, on the three-slip surface of water flow, you have floating things which float on the surface will start gathering into patches. And this is very important in the marine environment of the water surface. All these floating things, pollutions, as they start also gathering into patches. Now, there is also a possibility to have fully compressible flows, like with C=1 is called overdamped motion of Brownian particles. Yeah, let us not discuss it in more details right now. So once we go to that lecture, then we'll speak about that. So this is another lecture, is AIC, about compressible velocity fields. And then what's next? Then there are particles in fluid flow. So we have smooth fields, fractal fields, compressible fields, and then we have, but thus far we assume that the particles, the dye particles, are very small. We don't differentiate their size. But we have like dust particles. They are no longer, might not no longer be so small. They have some finite size, and they have some finite inertia. So AID is now mixing of inertial particles. What this might be like dust. But it can be also water droplets in the air. Droplets in the air. And in many industrial applications, you might also have. For instance, soot particles you burn incompletely, and then these are, and so on. So what happens with mixing of inertial particles? Actually, this to a certain extent it comes down to partially compressible velocity fields, because it appears that what we need to look at is not exactly the velocity field itself, but the velocity field which the particles move. The inertial particles detach themselves from the flow we now need to actually look at the velocity field of those particles, not the flow itself, or what does it exactly. And it appears that there appears a certain compressible path, then even if the flow itself is incompressible. All right, and this is more or less what we have at hand with the passive scalar fields. But then, what next? We have passive scalars, but we said that that's not everything there is. So there are also actually the possibility of having something else. And so what is the next option? Vector fields, exactly. But what would be the easiest case of vector fields? Vector, temperature is scalar. Only one number. I'm not asking right now example, but like in terms of classification. So remember, we have active and passive. So now the easiest case is passive vector fields. Now this is now A double I and A is passive vector fields. And that is actually only one example. And it might be difficult for you to figure out, but still I give you a chance. What might be a passive vector field which can be mixed with a flow? Be like maybe some sort of like radiation or something that is like only in like one direction. No. All right. But I think it's better if I say magnetic field. So magnetic field is vector field, right? And magnetic field, if we have perfectly conducting fluid, like plasma, for instance, we have plasma with good conductance. And then magnetic flux is so called, we can say that it is frozen into the fluid flow, plasma. So we have a magnetic field. And plasma flow. Plasma, but it can plasma flow, but it can be also like something which conducts and is in fluid state, liquid state, like liquid sodium, for instance. So you know what is sodium? So like metal. As well. Why it is that way? Because you know and phi is a flux, magnetic flux through liquid or material, a special contact which you take. And now, if liquid flows and you mark a material loop, you mark a line on the fluid. Imagine marking all the molecules, and then you can observe the magnetic flux. And if it were to change, you would have electromotive force through that contact. But if conductivity is very good, then this must be then this must be zero. So this equals to conductivity, integral conductivity, and times electric field. No, conductivity. Conductivity. I write the first I write it like a conduct integral of EdL. Material law, but I substitute now E from Ohm's law as integral and rho J dl. But if rho equals to rho equal to 0 if rho is 0. So if you have a perfectly conducting fluid, then you cannot have electromotive force because otherwise you would need to have infinite currents, which you won't have. And because of that, magnetic flux through material contours is conserved. Yes?
Could you just in case explain what is rho exactly?
Rho is resistance, resistivity. Rho is resistivity of the fluid. Okay.
Eesti keeles on see eritav.
Yeah. And so, if you have a plasma flow, then actually magnetic field is being transported by the fluid flow. And it appears that actually this effect is what is causing all the magnetic fields in the open space. You know, stars have magnetic fields. You have interstellar space, you have magnetic fields. And all these are caused actually because of this effect. And more specifically, if you were to have a perfectly conducting fluid flow, but no magnetic field, then that would be unstable. Because if you assume a certain perturbations, like molecular perturbation, you have suddenly some magnetic field, then it would start to grow because of this effect. Well, there would be no possibility for it to grow in 2 dimensions, because in 2 dimensions, and if a flow itself is incompressible, then magnetic flux is transported. Just you have here somewhere take a loop and it's transported, and so just the magnetic field value is carried over and nothing happens. But in 3D, you have you mark a loop, but fluid flow can start going into 3rd dimension, and so this loop starts shrinking. And if it starts shrinking, flux must be constant. Surface area goes down, and magnetic field goes up. And that's in such a way you can create magnetic fields from nothing. Basically, it's like unstable, and that's why you have in open space magnetic fields. Well, we'll be speaking about this more specifically in more details once we arrive at this topic here. Well, now passive or active. You have a passive vector field for this effect when you have a magnetic field is very small, because if magnetic field grows big, then magnetic field itself starts affecting the flow. But in the so-called kinematic stage, you have a passive vector field. So passive, if B magnetic field is small. If magnetic field is small, then it can be considered as passive. And if we speak about instability, how magnetic fields emerge from nothing, then this happens when you have at the first stage you have no magnetic field and then starts growing, but it's still very small, and then it works as passive, and this is called kinematic magnetic field. Magnetic dynamo. Dynamo means you generate something, right? Magnetic dynamo, magnetic field is being generated by projectile. There are also experimental devices which study this magnetic dynamo. Like in Riga, there is a big facility where they have exactly sodium, liquid sodium, and they try to generate magnetic field out of nothing. But then at the end of the day, magnetic field grows big, and then it is no longer passive but active. Like, for instance, if you have Earth as magnetic field, and there, of course, field is big enough to affect the flow, and then it is active, vector field problem. But now we don't discuss active magnetic dynamo, active magnetic. We won't be discussing the case of the magnetic field is so big that it's no longer a kinematic and vector field becomes active. Why? Because just too mathematically too complicated and mostly done numerically. And our aim, let us keep in mind, is to have just a qualitative overview of things. So if we were to go there more details, it would be just it won't give you much additional insight into that. So we stop at best. Yeah. Okay. Yes.
We have some break in the middle of this as well.
Are we gonna take all 16 lessons?
Sorry?
Are we gonna take all 16 lessons by?
Well, not so. What is the time now? We have been here with you 1.5 hours. So my suggestion is let us try, because beginning was like we didn't just discuss too difficult topics like organization and all that. My suggestion is let us try to make it like finish it in half an hour, within half an hour or so, in 25 minutes, right? And then that's it for the day. So I think 5 minutes before the end, there is not much sense to make break. Are you okay with that? All right. So we are not going to. Well, some of those topics here might spread over more than one lecture. So just the keywords or topics which we'll be discussing, and there are. With that, we have finished more or less with passive fields. Now, what is left to do is active. And now, when we go to active fields, it's mostly, well, we also learned here that actually magnetic dynamo problem can be active. It's a problem of mixing of active field. But the of most importance is the turbulence itself, because I started with saying, let us recall that turbulence itself is mixing of a vector field. And now here, let us go to that. Now, with that, therefore, we have more or less finished with this topic A, and let us write here now following. AIIB would be the active vector field. A double I and B active, mixing of active. But that actually is the same as turbulence. Which actually we denoted by B. A double I, B is actually the same as B, which is a turbulence. And how come? Well, it's quite easy because if we have hydrodynamic turbulence, you remember what we said about the magnetic field. So we had magnetic flux was conserved through material contours. But in the case of hydrodynamic turbulence, we have conserved vorticity of the velocity field. So we introduce a certain vector field omega, which is curl of a velocity. And then what is conserved is a flux of that thing, which is called now vorticity. Omega dl over material conductivity is constant. And because of that, actually turbulence problem itself is a problem of mixing of vorticity, but this vorticity itself very much depends on velocity field V. So it is completely active. No way around, this is active. Now, you can have different options for frozen quantity. For instance, magnetic, magnetohydrodynamics, MHD. Magnetohydrodynamics. Dynamics, hydrodynamics. We have an integral of B dl is constant. But there is also possibility to call electromagnetic hydrodynamics when you have still the different combination. So-called EMHD, electron MHD. I'm not keeping like more details what is the EMHD about, but in that case you have something like omega would be basically omega would be B minus Laplacian of B. Which properly chosen units, you have a B minus Laplacian B flux of it is concerned. But actually, this is, we are not going to discuss too much, but the thing is that in those cases, you can have turbulence for MHD and for hydrodynamics. But what we'll be discussing here, actually, with you is this thing here, hydrodynamic turbulence, where omega dl is conserved, where omega is like this. This is our topic. Topic for B. B is here. And now what we'll be doing with hydrodynamic turbulence is I cannot do much because it's very complicated. Feynman says that turbulence is a last unresolved problem of classical physics. And it is indeed complicated, but what we'll be doing, things what you definitely need to know is now as for B, B is Kolmogorov. Kolmogorov scaling. Cascade, energy cascade. Just saying keywords here because we have specific lecture on that energy cascade. Now this is for 3D flows. But it appears that 3D hydrodynamic turbulence and 2D hydrodynamic turbulence are in that term completely different. And the reason being that in 2D and you have additional conservation law. So if you did not have any dissipation, then what is concerned, of course, is energy. So a Kolmogorov scale energy cascade is actually based on the conservation of kinetic energy as long as unigalactic friction. So basically energy square the cube r integral of velocity squared is constant as long as no dissipation, no friction. It is very always. But in 2D, you have actually additional law, and in particular, that omega square, omega which was defined before, the omega square dq is also conserved. And this is called an entropy. So in 2D, you have also an entropy conserved, and because of that, you cannot have so-called direct energy cascade. Because of that, energy cascade needs to be inverse energy cascade. What does it mean, inverse energy cascade? It means that in the case of direct cascade, if you input energy at certain large scale, make a large vortex, what happens with it is that it breaks down the smaller vortex energy of large vortex, comes later on energy of smaller vortices. So energy cascades down to smaller vortices, this direct cascade. But because in 2D you have entropy also conserved, this cannot happen. This is forbidden for the secondary conservation. And then the only way for vortex energy is to go to bigger scale. So energy of small vortices join, forming big vortex, and this goes to big vortices. That's why you have actually the cyclones and anticyclones. We have cyclones and anticyclones are big vortices. This is because atmospheric flow is basically 2D in big atmospheric flow in big scales. Very big scales 2D. And because of that, inverse cascade. and because of that, cyclones and anticyclones, big vortices. Okay. So this is now our topic, VRR. And then we still have some few things which I didn't actually when we discussed those passive scalars. I think I skipped few topics. We might have also separate lecture. I can just write here keywords like we have for passive scalars. What I forgot from before to mention is one more thing. One more thing. PIII. Intermittence. Intermittency, Kolmogorov scaling means actually that the field lines are fractal. Actually, we learn just, I'm not going into details right now, but you will learn that direct cascade means that fractal field lines, because energy of big vortex goes to energy of smaller vortices. So you have all smaller and smaller vortices, which are, means that your velocity goes also along very small curved trajectories. And that's why you have fractal field lines. But this is not the full story because you have intermittency. So if you take smaller vortices, they are not all the vortices are of the same intensity, but some small vortices are much more intense than the others. And this is also something which also was realized by Kolmogorov and what we call intermittency, that size distribution, intensity distribution is no longer Gaussian, but it is like has power or tails. Non-Gaussian, that we fix of velocity. Non-Gaussian, Gaussian velocity increments. Distribution of velocity increments. And yeah, that's mostly what we'll be discussing with the turbulence. But then yeah, a few topics which I mentioned before is not specific laws like it goes for A something is Richardson law. This tells about so-called peer dispersion of particles. Like if we take two particles that flow and look how the distance between them grows. So if here the distance between them is L as a function of T, if we have fully developed turbulence, then this one here grows at a T to the power of 3/2 in accelerating manner. So we'll be deriving this. So E is Kolmogorov law. It fully developed turbulence. This means that if we have smoke trace from chimney, then the diameter of the smoke trace grows according to this law. If you have wind blowing and then like chimney, smoke from chimney. And then we have a bachelor's law. But I'm not going to explain right now what is bachelor's law, because it will be a little bit more to explain, but it also has to do with passive pressure. Bachelor's law. Yeah, one more thing which I forgot, actually, there is still a little more to be. For B is about actually so-called weak turbulence. Right now, what we discussed here under B, this was a so-called strong turbulence. Now this is now out of the screen. I think I'm correct. But this is a strong turbulence, maybe up here. So this is strong turbulence. So what is strong turbulence and weak turbulence? Strong turbulence is when you have so a long-lived structure like vortices, coherent structures. Coherent, which means that you have like a long surviving coherent structures. What might be coherent structures are vortices. Can be solitons. And maybe something so-called actually some singularities. Maybe, for instance, solitons in certain cases can collapse, like energy singularity forming some singularities. We are not going to deep into those singularities, into those things, only briefly mentioned. Only briefly mention them. But if there is strong turbulence, there must be also weak turbulence, right? So we have actually IV, which is very weak turbulence. Weak turbulence. And what is weak turbulence? Weak turbulence is based on perturbation surface. So all this turbulence itself is completely nonlinear. So actually, this everything here nonlinear, strongly nonlinear. And the reason, since they are strongly nonlinear, this is exactly what makes it mathematically difficult, and why we are not going to mathematical details. Because just nonlinear, to study properly nonlinear thing is mathematically very difficult, most often impossible, and you only need to go to numerics. Strongly nonlinear. But in certain cases, you can have things which are nonlinear, but only slightly. Yeah, we need to finish actually, but we are already almost there. So, so if you take ordinary waves, linear waves, like on the surface of water, simple wave, it is linear structure, it propagates nicely and no irregularities. This is no turbulence. Now, wave, linear wave, regular, no turbulence. But if amplitude grows, it becomes slightly nonlinear. And then what happens is that two different waves start interacting. And what might happen is that energy from one wave starts getting into bump into another wave. You can have wave interactions. Now, slightly nonlinear. Non-linear. If amplitude grows. If amplitude grows. So waves start interacting. And so energy of certain waves will start getting pumped into other waves. And this is what is called weak turbulence, when you can construct a theory based on perturbation theory. So you consider this these interactions, nonlinear interactions, as perturbation and calculate. So this is perturbation theory. And just keywords which we will be discussing here are plasmons, phonons, like those quasi-particles. You can discuss how energy is pumped in terms of those notions. Plasmons, phonons, mostly those. So the so-called four waves interaction, when two waves interact to giving disappear and two new waves appear. For instance, you have heard about so-called stories that ninth wave is bigger than the others. So actually it appears that if you build a perturbation theory for water waves on deep water, then this also predicts that actually there is like periodicity that roughly speaking, every ninth wave is bigger than in between, more or less. All right, and that's basically now all the topics. So we slightly also discuss weak turbulence, not too much. This is like one of the quite short topics, because going deep would require much more time, just so that you have some idea about these things as well. So we are trying to give you a wide overview over all the topics, because we take like a very round and wide tour around it. So in some topics, of course, we have not had much time to discuss, but the aim is still to explain you and give you a qualitative idea about those things. All right. So any questions? What more or less what I explained you right now, the topics more or less understandable? More or less. Yeah, because we are going into details during each of the lectures. And now, should we also try to appoint who will be doing a presentation next time? Who is brave enough?
We don't have the groups yet.
We don't have the groups yet, but all right. So, but there is not much time to discuss. So I'll be sending maybe. Maybe some spreadsheet to create for you, Google Docs spreadsheet to share with you. I can fill in topics apart from the overlay, which I'll be sharing. Maybe that would help. Of course, you can do it by yourself as well. But
how are you the online students that your students for
basically, you need to communicate with them. You can make a personal appointment with them, or just discuss like chatting in the overlay for however you want. And they are making presentation over Zoom, of course. Sorry?
Most of them are here, right?
So we need to try to get in touch with them our email, because today they were not.